In this video, we're going to take a look at the activity results and calculations for the Boyle's law and the ideal gas law labs we did in class last time. For the Boyle's law graph, one of the things that I wanted you to get from doing that activity was that it is an inverse relationship. If the pressure goes up, the volume is going to go down, and vice versa. And we did that by changing the volume of the syringe and reading what the pressure measurements were on the LabQuest instrument. The graph is a hyperbola, and we are going to see that if you go back and look at your algebra textbook, the graph of that should match up with what that topic is going to represent. And the relationship is the pressure times the volume is going to equal a constant. So if the pressure goes up, volume goes down, and the K value we would be able to determine from this graph. Now, if our data was better, we would be able to actually do that, but our instruments have little gas leaks and the calibration isn't perfect, so that determination for the constant would be difficult for us to accomplish. Let's move on to the ideal gas law. First off, make sure we got our data correct. You have a mass of the lighter before the experiment took place. You took a temperature of the water in degrees Celsius, which you will later need to convert into Kelvin. You have the volume of the gas in the graduated cylinder, and you measure that in milliliters. You're also going to have to change that into liters later on. You have a mass of the lighter after you have dried it for the first time, and then the second time, if you had a mass difference greater than 0.01, I believe, between the first and second reading, you were supposed to do it a third time. You will be using the last measurement that you made for the mass in calculations later on. We also had a pressure measurement of the room, and this is going to represent the pressure of the gas that we collect inside of the graduated cylinder. Now, the thing is, the instrument that I have used to measure the pressure in our room measures it in inches of mercury, but we're going to need to later on change that to millimeters of mercury. You also then looked up via a website the vapor pressure of water, and that website gave you the pressure of water in millimeters of mercury. With all of this data now, we can go through and do the calculations to help determine what the value of R is. So the first calculation that we're going to have done is the mass of the butane used. Now you're going to use the masses that you measured in the experiment to determine the mass of butane used. Once you have determined the mass of the butane used, then you can calculate the moles. And this is going to be a gram to mole conversion. Add up the mass off the periodic table for butane and convert that grams to moles. Make sure you use your dimensional analysis and set the problem up so that you can show how the units cancel and get the correct unit of moles. Also, make sure you use the correct number of significant digits. I believe that you're going to have 4 significant digits in the mass of the butane after you've done the calculations, so you should have 4 significant digits for your moles as well. Now, for the pressure of the dry butane, one of the things that is mentioned in the text of the lab is that we are collecting this gas over water, and when we collect a gas over water, we are literally going to collect 2 gases. We are going to collect the water vapor that's caused by the evaporation of water, as well as the gas, the butane. We need to make sure that we're measuring just the pressure of the dry butane. So we're going to use Dalton's law of partial pressure, which I have here, and you're going to plug in your pressure for your water vapor pressure and the pressure of the atmosphere. Now, the problem with that is that you have 2 different units. So again, you're going to need to make sure that you're converting from the inches of mercury to the millimeters of mercury. You're given a conversion of 2.54 centimeters equals 1 inch, and then so you can convert that inches of mercury to centimeters of mercury, and then you can convert that centimeters of mercury into millimeters of mercury. Once you have the pressure of the dry butane, you're then going to convert that into atmospheres. And you have those conversions listed in the document that you worked on a few class periods ago dealing with pressure. Two other calculations you need to take care of is make sure your temperature is in Kelvin. Remember, the conversion for that is degrees Celsius plus 273. And then also make sure you have your volume in liters. We are then able to actually now use these values and plug into this equation PV equals nRT. That is the ideal gas law, and there will be another video going over why that gas law is special and how we can use that. But for right now, we're going to calculate what the value of R is. R is what we call the ideal gas constant. It's a very important constant in chemistry and physics. We have the pressure of our dry butane. That's going to be our P in the equation. We know the volume of the gas. We're going to use the liter volume and plug that in. We know the moles of butane, and we also have the temperature. Plugging those four variables in, we would be able to calculate for the value of R. Once you have that R value calculated, and hopefully it's around 0.08, due to how we're conducting the experiment, there is going to be some variation, but hopefully it's not too far off from that. I want you to go and report that R value in a spreadsheet that I will have up on my big campus. The last thing that you're going to do is you're going to calculate your percent error. Now, what we want to do is we just simply see how far off are you from the actual value. Now, the actual value is 0.0821, and the units for this are atmosphere liters divided by mole kelvins. Now, it seems like a very unwieldy unit, but you will see later on why it's important to have that unit. So our percent error is simply going to take your experimental value. So the R value that you calculated is the experimental. You're going to subtract the 0.0821 from that and take the result of that difference and divide it by 0.0821 and multiply it by 100. This will give you your percent error for the experiment. Hopefully your percent error is around 10% or less. If it's not, by all means, don't worry about it. One of the things I want you to do is from this activity is have gathered some information and practice doing calculations with those. Hopefully this answers all your questions. If not, please contact me so that we have this information ready to go by beginning of next class period.